Cet appel est désormais enregistré.
All right, so hi everyone. Welcome to this year's last South American geometry webinar. Today or tonight, depending on where you are, our keynote speaker for the year will be Eveline Legendre. Eveline has recently deepened ties with South American mathematics in a number of collaborations, so a Math and Soup project and FAPES PNR collaboration, which she coordinates on the French side. Also, on that note, a word from our sponsor. We're organizing a very nice conference for the Bridget collaboration, which will be in France next year in beautiful Corsica. The link to be found on the chat. Also, Luis, can we please have the instructions on the chat? There you go. So if you wish to subscribe to this webinar, you can send the word webinar to our email, or you can join the announcements WhatsApp group. And furthermore, you can add via the link, you can add this recurrent event to your agenda. There will be no visible further events this year, but the same agenda will be reproduced for next year's round of talks. So without further ado, let's please welcome Eveline telling us about the Einstein Hilbert functional and the Donaldson-Futaki invariant. So please, Eveline, can we do 50 minutes plus discussion?
Yes.
Cool.
Okay. So I start.
Please go ahead.
Okay. So thank you, Enrique and the other organizers for the invitation. So I will talk about joint work with Abdellah Lahdilli and Carlo Scarpa. They are both postdocs in Montreal right now. And so our work is about the Einstein Hilbert functional and the Donaldson-Futaki invariant. So I will explain well, most of the talk will be explaining the setting in which we're gonna work. So the problem I'm interested in is is given a complex compact manifold M polarized by an ample holomorphic line bundle, is there a constant scalar curvature Kähler metric omega in the Chern class determined by the bundle L? Just to be sure that we're on the same page. So what that means is that the scalar curvature of the matrix and the Riemannian matrix associated to the form is a constant. This constant is actually determined by some topological invariant of the manifold, namely the first Chern class, so the complex structure, and the first Chern class of the line bundle. Just to be sure that I recall that a Kähler structure is let's say a triple of a complex structure that can be encoded in an integrable almost complex structure that I denote J, and a 2 form which has to be closed, and 1 with respect to J. So being 1 means simply that omega, when you put J in each entry, it still give you omega. And also there's a positivity condition that typically we write just omega greater than 0, which actually makes no sense. What we mean is that when we put J in 1 in the entry, so the almost complex structure 1 of the entry, this is a Riemannian matrix. Okay, so this is a setting. So typically we will say that omega is a matrix. Well, it's not a Riemannian matrix, but when we compose with J, it's a Riemannian matrix. And so the scalar curvature is the trace of the Ricci curvature of the Levi-Civita connection associated to the Riemannian matrix. Again, composed with J, so it gives a 2 form, and we take the trace of this 2 form, and then this is this is a function. So this thing is a function, and we look for the matrix such that this function is constant. Okay. So the problem of finding a cscK matrix in a given class is actually it's an old problem. It's a particular case of a more general problem set by Calabi in the 80s, where he defined, he considered this problem for a more general matrix, which are extremal matrix. But even in that case, for the cscK case, it's still a very hard problem, let's say, and it's been working on by many people for the last few decades. And maybe you heard about the Yao-Donaldson conjecture that predicts that there exists a solution, so there exists a cscK matrix in the class, if and only if the pair, so M, the complex manifold with its sample line bundle over it, is K-stable. So this condition is an algebraic condition that I will not define in details, but I will talk a little bit about K-semistability, where it involves the Donaldson-Futaki invariant that appeared in the title of the talk. So this conjecture is not completely solved, although there's been very great advances in the last few years. So in particular, Cheng solved, let's say, the differential part of this conjecture. So there's a lot of, we can talk about this for hours and hours, weeks, maybe months, because there's many things to say. But our approach with Abdellah and Carlo is a little bit, let's say, transverse to the mainstream direction actually taken by people. So I will not have to talk about all those great works. So let's just say that for Fano manifold, and when the line bundle is the canonical bundle or power of it, it's completely solved. So in this case, cscK matrix are Kähler Einstein matrix, and it has been so the Fano Yao-Donaldson conjecture has been solved 10 years ago, and there are now many proofs, starting with Chern, Donaldson, and Chern and other people. And so the reason why it's interesting is that these K-stability or these Kähler-Einstein matrix tells us many things, or gives us tools to do the moduli space of K-stable Fano manifold. So maybe another thing I should say is that for these two cases, there's no obstruction, and the solution, the fact that there exists a Kähler-Einstein matrix, is a consequence of an older theorem, which is due to Calabi and Yao and also Aubin. And so in that case, there's no obstruction, and so the case which was more difficult is the Fano case, actually. And so in this case, it's when they are all interesting, but this was the one that was more difficult. So as I said, the direction we took with Abdellah and Carlo is a bit transversal to all these works I've been mentioning. And the first motivation, if you want, comes from the basic case, so the case where M has dimension 1, complex dimension 1, so it's a complex curve. So in that case, it has been solved by, the problem, the cscK problem was solved by Poincaré, so many years ago. And so what he proves is that each simply connected complex dimension 1 manifold admits a compatible cscK matrix. So in this dimension, the problem is much more simple due to the following fact, is that in this dimension, a complex structure is equivalent to a conformal class of Riemannian matrix. Okay, just because, this is just a basic exercise. It's just a basic exercise, so that biomorphic transformation are conformal transformation or biomorphic in this dimension. And so, the problem reduced to study a conformal class of matrix, and the cscK equation, so the scalar curvature of the matrix. So the curvature of this matrix actually will be given by this equation, and so you want to solve equation which can be solved. Okay. So, of course, this strategy does not work at all for higher dimension, because in that case, if you take a closed form, like Kähler form, and you multiply it by a positive function, that this one, this new form will not be closed anymore, right? And unless f is constant. F is constant. So it doesn't make any sense to try to apply a Poincaré strategy for this thing. And so our idea can be thought as trying to adapt Poincaré strategy in higher dimensional setting by going to another space, a circle bundle over M, and and then consider a conformal transformation and try to solve the problem in this setting. And so, yeah, the main part of the talk will be just to explain this this strategy to you and the object involved in our work. Okay, so I start with a complex polarized compact manifold with L always a line bundle, and I considered a circle bundle associated to it. Actually, for a technical reason, I take the dual of the line bundle and the associated circle bundle of this dual. Okay, so in this dimension, I can consider explicitly like I did. So I take off the zero section quotient by the radial action. But this is a classical fact that given a complex line bundle, you have an associated circle bundle. This is just this circle bundle. And for the rest of the talk, I will name Xi. So Xi will denote the generator of the circle action on N. So because I have a complex structure on L, and it's a complex vector bundle, there's no ambiguity, and Xi is well defined. There's no ambiguity on the orientation I'm taking. And I also fix a transversal holomorphic structure. So a transversal holomorphic structure, this is something which is defined more generally, but in our setting, it's just really the complex structure on M, but seen as an endomorphism on this bundle over N. Okay, so Tn quotiented by the real line bundle induced by Xi is a bundle over N. Okay. And the reason why I'm calling it transversal holomorphic structure, because actually what I just defined, actually it makes sense for a marginal transversal holomorphic manifold of Sasaki type, with Xi being not necessarily regular, so not necessarily inducing a S1 action, but lying in the Lie algebra of a compact torus. A compact torus that preserves the transversal holomorphic structures. Actually, all I will say until the end, well, maybe I can tell you when it's stuff to be true, but everything I will say from now until, let's say, in 40 minutes or 30 minutes, will be valid for a general Sasaki manifold. Okay. And so I will consider the space of contact form with the Reb vector field, all the same Reb vector field Xi, and such that the external derivative of the contact form is 1 with respect to this transversal holomorphic structure. Okay, just to be sure that everybody follows. So a contact structure means that when I wedge eta with d with its differential times n, so n is just the dimension of the complex dimension of m here, is not zero. So it's never zero, and so it's positive with respect to the orientation I have anyway in my setting. And the fact that the Reb vector field is Xi, what it means is that actually for any contact form like that, there exists a unique vector satisfying the following two conditions. When I evaluate the form on Xi, it gives 1, and the form is invariant, is an invariant of this vector field, so it's constant along the flow. Okay. And now, so it means that d eta, so these two conditions implies that the differential, so d eta is basic, psi basic. So d eta is a psi basic form. And so it makes sense. It's well defined on the quotient bundle, Tn over xi, and so it makes sense to ask it to be 1, 1. So because I'm defining everything, let's define what's a basic form. So a xi basic form satisfies the following. When I contract with xi, it's 0, and it's also constant along the flow of xi. Okay, so this is the basic object. Okay, so as a matter of fact, all these structures here are Sasaki type, for those of you who know what it means. So they are all Sasaki because Xi preserves the transversal holomorphic structures. Okay, and so why I'm interested in this space of contact form, it's because actually it will give a good parametrization of all the Kähler, the Kähler form in the first class of the bundle. Okay, so for all form in this set X, there exists a unique Kähler matrix such that its pullback for that bundle, right, is the external derivative of the form eta. Okay, so that means that I have a bundle here. I have a map actually, and it's easy to prove actually that this vibration from one contact form to or one Sasaki contact form to a Kähler matrix downstairs, it's surjective. Okay, and so here it's just the space of Kähler matrix, right? This is just the Kähler matrix I'm interested in. Okay, so as I said, this map is surjective, and the kernel are only the closed Xi basic forms that will not interfere in the curvature I will be considering anyway. So so this is the set I'm interested in, and now I will take conformal transformation of this set. So I will consider Z the space of all the conformal transformation of these contact Sasaki form with fixed reb Xi. Again, this is a bundle. Z is a bundle actually a trivial bundle over X, and the fibre arch is just the smooth function on the base manifold, or in the marginal Sasaki case, the T invariant function. Okay, so and so this is the space on which I will be working. Another remark I want to say is that each form here, each form in Z, so in the bigger space here, actually defines a unique CR structure, because I have fixed the transversal holomorphic structure. So there's only one endomorphism of the contact structure, so the kernel of the form, that lifts this transversal holomorphic structure. Okay, so it means that these sets, this bigger set Z, I can consider it as a subspace of contact CR structure. So it's not only gives a contact form, but also a CR structure. This is because I have fixed the transversal holomorphic structure. And also that this bundle map, right, I talked about, actually each fiber is the conformal transformation of all the contact forms compatible with one single CR structure. Okay, so we have really a bundle. So X is it's a trivial bundle. So I have this zero section, which is X, and then the fiber are each fiber corresponds to one CR structure. Okay, so what do I do with that? What do we do with that? Actually, we will consider. Well, we will try to translate the cscK problem in this setting, and we will see that it works. So, well, there's some things work. And for this, I have to recall what's the Tanaka Webster connection of a contact CR manifold. So given a contact CR structure, like the one in the big space Z I was talking about, there exists a unique connection on the tangent bundle 10, for which all the structure are parallel, so all the contact and CR structure are parallel, and the torsion satisfies some condition. So it's vertical and it behaves well with the CR structure. Okay, so what's interesting in this is that it's unique, actually, a bit like the Levi-Civita connection. But this one is not the Levi-Civita connection of the CR of the matrix, but we have a matrix. Okay, but the Levi-Civita connection of that matrix is not, well, I don't know if it's interesting, but it's not interesting to me for now. Okay, but I have a Riemann matrix, and I have a particular connection that I like, which is the Tanaka Webster connection, and then we consider the scalar curvature of that connection, which is the trace with respect to this Riemann matrix of the Ricci curvature of the Tanaka Webster connection. This is a function that we'll call the Tanaka Webster scalar curvature. Okay, and now the reason why it connects with the cscK problem is the following term due to Webster. So these terms are
Eveline, just
yes.
real quick. Alpha is eta, right?
So I try to make a difference. So eta typically will consist in a spatial, the spatial Sasaki type contact form, while alpha is a more general contact form.
So it's contact CR will be alpha, yeah?
Sorry, I didn't hear.
So alpha will be contact CR, which is more general than Sasaki.
Yeah, absolutely. Okay. Like, for example, alpha will typically denote F times eta. Or F minus 1.
Gotcha. Thank you.
Okay. While eta will be Sasaki type with a fixed rev vector field. Okay. So, for example, this rev vector field, I note psi here is not necessarily the psi I had at the beginning. I should have write it another way. Okay, so the theorem of Webster, is it okay to answer your question? Okay, so a theorem of Webster, so I think it's like in the 70s or 80s, is that when Xi generate a S1 action, so we say that in that case that it's quasi-regular, and killing, so killing means that, in my setting that it preserves the CR structure, or the transversal holomorphic structure, is enough. So let's say this way. Okay, so it preserves the matrix if you want, so that's why we call it killing. Then nabla is the pullback of the Levi-Civita of the induced Kähler structure on the quotient. Okay, actually in this situation, the induced quotient is actually Kähler and not only symplectic. Okay. And so, well, so in particular, the Tanaka Webster scalar curvature is the pullback of the scalar curvature of the Kähler matrix downstairs. Okay, so as a corollary of the Webster theorem, and in the particular setting we are in with this line bundle and everything, we can say that the cscK structures in C1L are actually the cscTW structure in this particular set of contact form, right? That I define. You remember there was this X which corresponds to Kähler structure downstairs, and and there's a bundle over it that I call Z, which is a bigger space. Okay, but the cscT W structure that happens to be in X are actually cscK structure, or corresponds to the cscK structures. Okay, and so this is just an observation from what was done before, but actually it already give us idea, like, okay, we would like to find a cscTW. If we can describe all the cscTW structure in Z, we will be able to say, oh, we have a cscK structure or not. Okay, so there was people who worked on this in the 80s, like given a CR structure, do we have a cscTW metric on this? And these people, I would write their name. There's Jerison and Lee, Gamara, and Yakub. So it's different. It was not so easy. And they proved that given a CR manifold of contact type and a conformal class of contact structure, there always exists a cscTW metric. We needed to work a little bit to adapt to our situation where we want the cscTW structure to be also invariant by the circle action, the spatial circle action we have from the fiber of L. But still, we adapt. We were able to adapt the result and prove that actually on each fiber we have one cscTW. Okay, so we know that there is a cscTW. And so what does we don't have uniqueness, but actually we know that uniqueness is not true. But the first observation actually we can make now is that actually the cscK problem can be seen as an intersection problem in an infinite dimensional space of contact CR structure. Okay, so we have let's say the section, although it's not necessarily a section, of a cscTW structure, and we want to see if it intersects this space X. Okay, and so Jerison, Lee, Gamara, Yakub, they worked to prove the result, and prove the result. Actually, we worked with the Einstein Hilbert functional, but for the Tanaka Webster scalar curvature. So let's be more precise. So the Einstein Hilbert functional in this setting, that maybe we should call Tanaka Webster Einstein Hilbert functional, it's a bit long, is the total scalar Tanaka Webster scalar curvature divided by some power of the volume. Okay, so let me be here. So here the numerator, so the thing on the top is the total scalar curvature. It depends on the CR structure, but the CR structure is determined in my setting is completely determined by the transversal holomorphic structure and the contact form. So I don't need to put the contact structure in the notation. And here is the volume to some power. So the reason why we put this power is because we want the Einstein Hilbert to be functional to be invariant by just multiplication by a constant. We want to be homogeneous on that space. Okay, and so this is the Einstein Hilbert functional, and our theorem says that a matrix is cscK if and only if the corresponding contact form in this subspace X, like the zero section and then this infinite dimensional space, is a critical point of the of the Einstein Hilbert functional on that bigger space. And then also, moreover, the critical point of the H are cscTW, so constant scalar, our contact CR structure with constant Tanaka Webster scalar curvature. But moreover, their killing, their associated red vector field is necessarily killing, okay, which is a big condition, okay. It's very that makes it like in a finite dimensional space of structures. And another way to say this actually is that the critical point of the Einstein Hilbert fractional are constant scalar curvature Sasaki matrix or structures. Okay, so here to be completely this is the CSCS matrix that commutes with this given red vector field F in the circle action of L, right? And so yes, so this is someone you.
Yeah.
Yes. Okay.
Do you have? Is there a meaning and interpretation to the absolute minima? Do they have some sort of topological characterization?
Good question. So this is so is it a minimal result? So the thing is, the one thing which is not so well was so nice with the Einstein Hilbert functional is that this functional is not convex.
Huh.
So we have examples that we've built years ago of multiple critical points. So, like for example, there exists Sasaki manifold with a rep cone admitting different CSCS matrix that are very different. Okay, and so it's not necessarily minimal. All that to say that it's not necessarily minimal.
Cool.
I can, if you want, I can come back over it later.
Very interesting. Okay.
Okay, so it's not minimal, but this is a critical point. So maybe, but so actually, in the case where the automorphism group is discrete, then the critical point will be the cscK metric of ML, because we will not have other killing vector field, other than just psi. So okay, so let's discuss this this result and the proof. So maybe I should say right away. So this result is really just a direct calculation. Actually, we just compute the differential of the Einstein Hilbert functional, and we had the result. And the reason why it's possible to do this computation is actually due to a formula due to Lyon and Tano, and we proved it independently. And so actually we have an exact formula between the Tanaka Webster scalar curvature of the conformal transform. If I do a conformal transformation this way, I know that the Tanaka Webster scalar curvature will behave this way. Okay. I have alpha here, it should be eta. And so this is a very this is an exact formula which we can work with. Actually, if you go back to the quotient, this is an example of weighted scalar curvature, like my collaborator Abdellah Lahdilli worked on a few years ago and developed the theory of this kind of matrix. So we were able to work with this formula, and actually we can compute the variation along a vertical direction. Well, this computation can already be found in the work of Jerry Sunley, for example, and actually it's easy. It's not a big computation, but we see directly that if so again, I will draw the same picture as before. So I have X, that you can think about as the space of Kähler metric on the base, on M, and I have these fibers. Okay, maybe I can put it green. So I have these fibers, and so what this formula tells us is that if you are a critical point in the vertical direction, so in the fiber direction, then and then you necessarily have you're necessarily cscT W. Okay. Now, a new computation, which was not fun, of course, with people working with the fixed CR structure, is the variation along the transversal direction. So it means now that, well, I still get my this same picture. I have X, I have the fiber Y, and I take a variation with respect to transversal direction, okay, like this way. And now you compute the derivative. But so if the point where I compute the derivative is a critical point of EH, then I will this part will vanish because it's critical in the vertical direction, and I will be left with this part. And so now it's a well-known result. So that operator is the G and T invariant part of the Hn of F, and this is 0 if and only if F is a Killing potential. Okay, so it means, so in the contact setting, contact CR setting I'm working in, that F, if you look at the contact vector field induced by F, this contact vector field preserves the contact structure by definition, will also preserve the CR structure. Okay, and so this is a big condition. This is in a finite dimensional space. Okay, and so if this thing is 0, we have it Killing. Okay, so this is a proof. It's easy. But well, we were happy to see that it detects the cscK matrix. And of course, the next question, the next natural question to this. So okay, so the Einstein Hilbert functional detects a cscK matrix in the class. How does it relate to K-stability? Okay, so I talked about very briefly about the Donaldson conjecture, and so the natural direction from our observation was to try to consider the K-stability condition. Okay, so for that, I will talk first about the Futaki invariant. So when we have the Futaki invariant makes sense for a Kähler manifold on which act a torus. Okay, so here the torus I will fix omega first, and I will also ask the torus to preserve the complex structure. Okay, so it's also holomorphic transformation. And I pick a momentum map. So maybe I should say what's a momentum map. So the momentum map goes from M to the dual of the Lie algebra of the torus. And when you apply an element of the Lie algebra, and you take the differential, so it's going to give a one form. You want it to be equal to omega contracted by the vector field induced by the induced vector field on the manifold. Okay, so this is the momentum map. It should satisfy this. And so Futaki introduce a character actually on the space of holomorphic vector fields. So the version I'm giving is the real version. So where I have where it's not defined on the complexified action, but only on the real part, let's say. And it's this way. So it's the integral over the Kähler manifold of the momentum map applied on A times the scalar curvature minus the constant. This is the constant I talked about, the topological constant. Okay, just normalization. And so the theorem of Futaki actually is that that functional does not depend on omega. Okay, so that Futaki of L is independent of omega picked in the first class of L. So I forgot the 2 pi. 2 pi. Okay, and so well, okay, so this is a theorem. This is not easy to prove, but what we can say from this is that, okay, if there is a solution to the cscK problem, the Futaki invariant must vanish, because picking this cscK metric will give us that this part is 0. Okay, so if there exists a cscK metric, the Futaki invariant must vanish. So the other abstraction I want to talk about is K-semistability. So I will not talk in the all generality. I will, in our setting, we'll only consider like a smooth test configuration. And if you want to say it quickly, is that the Donaldson-Futaki invariant of any test configuration over ML is non-negative. Okay, so now I have to define Donaldson-Futaki invariant and test configuration. So a test configuration, ML over ML, is a polarized variety with a linearized C star action and a C star equivalent flat surjective map. Well, maybe I should flat surjective map to CP1 that I see as a compactification of C, and such that for all the fibers which are not over 0 are isomorphic as a polarized variety to the original ML, or the original variety I'm looking for. And then the central fiber is the fiber over 0. So in general, the central fiber is not isomorphic to the original polarized variety you started with. And then the Donaldson-Futaki invariant is essentially the Futaki invariant of the central fiber. And so K-semistability say that this should be greater than or equal to 0. Okay. So there are other abstractions and finer abstractions. So K-stability or uniform K-stability, but I will not discuss about these other. Yeah, the other thing I said, which I think is important, is that now it's well known that if you have hope to prove the Yautz and Donaldson conjecture, you need to work on you need to admit non-smooth but normal polarized variety as test configuration, and also ask curly L to be not necessarily ample. Okay, but we won't. I won't discuss this part now, and I will always assume that test configuration is smooth and ample. So, how does the Einstein Hilbert functional relate to these abstractions? So a few years ago, with Charles Boyer, Yang Huang, and Christina Friedman, we have proved that the Einstein Hilbert functional is actually detects the Futaki invariant itself. Okay, so I talked about the Kähler version of the Futaki invariant. There's a Sasaki version, and it has also very nice properties, but it depends on the rep vector field. Okay, but only on the rep vector field, not on the other variation. In particular, in my setting, the transversal Futaki invariant of I can pick any form in X, and they will all have the same Futaki invariant because they all share the same rep vector field. Okay, so motivated by the fact that the Einstein Hilbert functional detects the Futaki invariant, the natural step. So in this, maybe I should add, this reduced Sasaki rep cone is actually finite dimensional. So this is like a finite dimensional version, and so it detects the Futaki invariant, which is a good invariant, but not a finer invariant. is defined on a finite. It is defined on a finite dimensional space of the Lie algebra of the torus we consider. So here it's in the same situation. We fix the torus, and it's only a finite dimension. So to go further and to try to see a K-semistability, what I will do is that we will consider ample test configuration and the associated circle bundle over it, the same way I did before. And I will have now two vector fields. One vector field will be zeta, which consists the test configuration action, and so it's sent to the action non-trivial and standard action on CP1, and another vector field which corresponds to the action on the fibre. Okay, so I have two-dimensional torus action now. And now I picked an invariant function, an invariant contact Sasaki type form on the test configuration itself, and we noticed that actually this function is, if we take S small enough, actually it's always positive. Okay, so here it's just 1 plus S times the momentum map associated to the circle action of the test configuration. And so we can consider then another contact CR form on the total test configuration, and this is the one we will work with. So I'm trying to be a little bit fast here to get to the result because it's late. So all that to say that we define actually a curve, a two-parameter curve of our what we call it a ribbon. So it's two real parameter in the space, in the big space. Actually, we worked at the beginning. Okay, so for each test configuration, I have a ribbon with two real parameters of contact CR structure. And our theorem, so the main theorem, is that actually when we take the limit of this ribbon, we get a function which exists and smooth. So the limit is at the central fiber, right? Exists in a smooth function in S. Also, when we take the derivative with respect to S and evaluate at 0, then this is some power of the volume, something constant, something positive, sorry, and constant, and the Donaldson-Futaki invariant of the test configuration. So so that means that actually, indeed, we can understand K-semistability with the help of this Einstein Hilbert functional, and actually K-semistability means that S equals 0 will be a minimum of this curve we get at the end of a test configuration. So well, I will stop here because I think it's been you asked me to give a talk of 45 minutes already.
No, 50 minutes. You can do 2 more.
2 more, but maybe yeah. So maybe I can just add that. So although the first theorem I presented was very just direct computation, this one was much more difficult to prove, and necessitated some work. So thank you for your attention.
All right, thank you. We can both clap or send reactions, which are very nice. Yeah, we can send reactions. There you go.
Thank you.
All right. Have you got any questions for Eveline? Comments?
About the functional in the first theorem, the critical points. What do you know about the second derivative? For instance, do you know that any critical point has finite index?
I don't know. I don't know completely because so we compute the second derivative in the vertical direction, and we see that actually the index. That's a good question. So it's going to be negative only if the first eigenvalue of the Laplacian is smaller than sum of the power of the scalar curvature. So if maybe I can try to be more precise. Let's just add a page. Okay, so what we will get is that the differential 2 of EH at S equals 0. So this is assuming that eta is CSCT, but not necessarily Sasakian. It's going to be some power of the volume. Okay, some power of the volume. Well, let's call it volume times m. And then it's going to be something like the Rayleigh quotient of the variation. Over n minus, so this is CSCTW, so let's assume that scale of eta is equal to c. It's going to be like c, and probably I'm making a mistake in the sign or something, but the idea is there. So here is going to be here's the derivative power 2 and the volume. Okay, so I think I'm mixing up the signs, so probably this way. So yes, so there's a minus in front. Okay, so you see that the negative eigenvalues corresponds to eigenfunction which have very small eigenvalues. Okay, and so it's finite dimensional. So yeah, so the negative space is finite dimensional for each CSCTW. Now, when we work on X, problems might happen because we cannot control this actually when we go in this infinite dimensional space of variation.
Yep. Good.
Okay. Thanks.
All right. We have a question from Brian as well. Brian,
well, I just was trying to make a reaction.
Sorry, I can't quite hear you.
I just wanted to make a reaction, but I missed it.
Oh, I see. You're trying to react. Okay, fine. We have a question from Christophe. Please go ahead.
Yes. Can you hear me? So,
yes.
Could you go back to your last slide? I mean, the one which is like 10 or 11. Yes. So you made a comment about your the first order variation, the end of the statement that the condition would be minimum, and it seems it's critical, right? The classical condition is the vanishing of the what you call DF of the Donaldson invariant. And so vanishing means critical for the Einstein Hilbert. So I don't understand what you mean by minimum for this.
Yeah, so I think indeed. So one problem is that the space of test configuration is not just well, it is not a linear space or convex space, or it could be very complicated. So we cannot say, oh, then because it satisfied this, it's gonna be critical.
I understand, but in any case, why is it linked to minima and not just critical points, right? The condition, the necessary condition we know is the vanishing of df, right? I'm missing something. That's right. I insist on what.
So the vanishing of df. So the vanishing of the Donaldson-Futaki invariant in general should correspond to product test configuration, right?
Yes.
Yeah, and so for example, because when we consider product test configuration, now it's linear because we can take the other version and we'll see that actually, so K-semistability implies that the product, the Donaldson-Futaki invariant vanishes on product test configuration.
Sure. Yes.
Because of what you say, actually, but because it's greater than 0 on one side, and then you take the variation on the opposite side, and then it has to be greater than 0 as well. So it has to be 0.
Sure. Yeah.
But but in the case where the test configuration is not a product, we cannot easily reverse the orientation just to get the vanishing.
I see.
So so actually I cannot. So I this is and so in this setting we would only ask for this.
I see. Okay, thank you for the comment.
Are there any more comments from the audience? If not, I have one. So Eveline, the way I would go about, the only way I know how to mass produce funnels, polarized funnels, would be, say, to look at weighted projective varieties of a carefully chosen degree, right? So I could choose, weighted homogeneous polynomials in some projective space, right? And they would be naturally polarized by the tautological polarization of weighted CPN. This way, these guys would be interesting because that's obviously because they're algebraic, and it should be easy to understand. Then a question here would be, can we express the critical points, or indeed the actual TW scalar constant scalar condition in terms of the polynomial data, right? So they're completely algebraic. So can we specialize your theory? Your theorem looks much too hard. So I find some aspects of it hard to visualize. But if I choose silly test configurations, which would be just families revolving around, say, these weighted projective polynomial funnels, do you think? Would everything be trivial? Is it possible?
I think it would be interesting to have more practical application, and where we can see on examples what it means. So I guess that the setting in which some kind of examples would be interesting. So I didn't talk about this in the talk because there are already things to say, but actually it's and this is in some sense very natural. This Einstein Hilbert functional actually is can be seen as we can prove that this is if let's see this way, if it makes sense, or like for example in the case where the central fiber are just orbifolds, then it's gonna be the total scalar curvature of the central fiber. Okay, but this S is because we are playing with the red vector field. Okay, so it's gonna be the not the total volume of with respect to psi, which actually anyway is only depends on the ML we've been choosing, but it's defined by invariant also, that you can see with Hilbert series and stuff like that. So we have already a candidate, and these coefficients of the Hilbert actually, so these A1 and A0 actually can be defined as the Hilbert expansion of some Hilbert series. This is done by Collins and Sasaki. And so what we proved actually is that this functional EHS actually tend to this these coefficients, the ratio of these coefficients. So I think that in the setting where we have polynomials, maybe we can try to find explicitly what is this function.
That's what occurred to me. Well, without this sophistication of the series, so I didn't have that in mind. I had in mind that starting with polynomial data should be the simplest case where you could sort of mass produce examples of a theory. And you're telling me this hasn't been done so far?
Not that I know.
Let's discuss this in France. I'll prepare something. I would be interested. Yeah. Okay.
Yeah, maybe we can try to discuss this. This would be a good idea.
All right. Cool. Interesting. All right. So if there are no further comments or remarks, let me stress that this has been a keynote talk for the year. Our 2023 cycle is finished. There will definitely be another cycle next year, but so please stay tuned for announcements around February or March. Adrian, did you have a word from the part of the organizers before we thank Eveline again?
So no, I would like to thank everybody who has joined us this year. I hope you have enjoyed all these nice talks that we have had. And I hope to see you again next year.
Absolutely. And so in the name of the organizers and everyone in the room, let's thank Eveline again and everyone who participated in the 2023 series.